A single turbocharger can force more air into an engine than nature ever could on its own, and that one fact changes everything about how modern performance works. Welcome to AutoVision Daily. Today we are breaking down one of the most misunderstood pieces of engineering in the automotive world: the turbocharger. Most people know the word. Very few people actually understand what is happening inside that housing when your right foot hits the floor. And here is the thing: once you understand the physics, once you see why this technology works the way it does, you will never look at a turbocharged car the same way again. We are going to cover the history, the mechanics, the science, and we are going to reveal one deeply counterintuitive truth about turbos that even experienced drivers get completely wrong. Let us start with context. The internal combustion engine, at its core, is an air pump. That is it. The more air you can push into a cylinder, combined with the right amount of fuel, the more energy you release when that mixture ignites. The problem is that naturally aspirated engines without any forced induction are fundamentally limited by atmospheric pressure. At sea level, the atmosphere pushes air into your engine at roughly 14.7 pounds per square inch. That is your ceiling. You cannot pull more than what the atmosphere provides. For a long time, engineers accepted that ceiling. Then they started asking what happens if you remove the ceiling entirely. The concept of forced induction is not new. Alfred Bucci, a Swiss engineer, patented the first exhaust-driven turbocharger in 1905. His insight was elegant. Exhaust gases leaving the engine are extremely hot and moving at high velocity. Instead of simply dumping that energy into the atmosphere, why not capture it? Why not use that waste energy to compress incoming air and force it into the engine at pressures far beyond what the atmosphere alone can provide? Bucci understood that this was essentially free power. You were recycling energy that was already being thrown away. Early turbos appeared in aircraft during World War I and World War II, where altitude robbed engines of dense air. Turbocharging allowed aircraft engines to maintain power at high altitude where the atmosphere was thin. The technology proved itself under the most demanding conditions imaginable. It took decades longer for turbos to migrate meaningfully into passenger cars, but when they did, the automotive world changed. The 1962 Oldsmobile Jetfire and the Chevrolet Corvair Monza were among the first turbocharged production cars. They were rough. The technology was immature. Turbo lag was severe, reliability was questionable, and the driving experience was unpredictable. But the foundation was laid. Through the 1970s and 1980s, Porsche, BMW, Saab, and others refined the technology. By the time Saab launched the Saab 900 Turbo, mainstream drivers began to understand that turbocharged did not mean unreliable, it meant more power from less displacement. Now let us get into the actual science. A turbocharger consists of two main sections connected by a shared shaft. On one side you have the turbine. On the other side you have the compressor. Exhaust gases from the engine flow into the turbine housing and spin the turbine wheel. Because exhaust gases exit a running engine at temperatures between 1200 and 1700 degrees Fahrenheit and at significant velocity, they carry enormous kinetic and thermal energy. That energy spins the turbine wheel at speeds that will genuinely shock you. Modern turbochargers spin between 100,000 and 250,000 revolutions per minute. For comparison, your car's engine redlines somewhere between 6,000 and 8,000 revolutions per minute. The turbo is spinning 30 times faster. That turbine wheel is physically connected via a shaft to the compressor wheel on the intake side. As the turbine spins, the compressor spins with it. The compressor wheel draws in ambient air and, through centrifugal force, accelerates that air outward. This accelerated air is then forced into a diffuser section that slows the air down and converts its velocity into pressure. This is Bernoulli's principle in action. You are converting kinetic energy into pressure energy. The result is compressed air being delivered to your engine's intake at pressures well above atmospheric. A modest turbo setup might run 7 to 10 pounds per square inch of boost. High-performance applications push 20, 30, even 40 psi or more. But here is what nobody talks about: compressing air heats it up. This is basic thermodynamics. When you compress a gas, its temperature rises. Hot air is less dense than cool air. If you compress air and then feed it into your engine while it is still hot, you lose a significant portion of the density advantage you just created. This is why intercoolers exist. The intercooler sits between the turbocharger outlet and the engine's intake manifold. It cools the compressed air back down, increasing its density, increasing the oxygen content per cubic centimeter, and making the whole process dramatically more efficient. Without an intercooler, turbo systems leave substantial power on the table. Now let us talk about the phenomenon every turbo driver knows and loves to hate. Turbo lag. When you press the accelerator in a turbocharged car, there is sometimes a pause before the power arrives. That pause is the time it takes for exhaust flow to spin the turbo up to its operating speed. At low engine RPM, exhaust flow is weak. The turbine cannot spin fast enough to generate meaningful boost. As RPM rises, exhaust flow increases, the turbine accelerates, boost pressure builds, and then the power hits, sometimes suddenly and dramatically. Engineers have spent decades fighting turbo lag. Variable geometry turbines, or VGT systems, change the angle of guide vanes inside the turbine housing to control how exhaust gas hits the turbine wheel. At low RPM, the vanes narrow the flow path, increasing gas velocity and allowing the turbine to spool up faster. At high RPM, the vanes open wider to allow maximum flow. Diesel engines pioneered VGT technology because diesel turbos face particularly complex demands across a wide RPM range. Today, VGT turbochargers appear in both diesel and gasoline applications. Twin-scroll turbochargers are another solution. A twin-scroll design separates exhaust pulses from different cylinders into two distinct channels within the turbine housing. Instead of allowing exhaust pulses to interfere with each other, twin-scroll turbos use each pulse more efficiently to maintain turbine speed between pulses. The result is faster spool-up and better response across the RPM range. Electric turbochargers represent the next frontier. Companies including Garrett, Borg-Warner, and several OEM programs are developing electrically assisted turbos where a small electric motor on the turbo shaft provides instant spin-up before exhaust energy takes over. Audi pioneered this in production with their 48-volt mild hybrid systems. The electric motor eliminates lag at low RPM entirely. You get turbo response the moment you touch the throttle. As engine speed and exhaust flow increase, the electric motor phases out and exhaust energy takes over. It is a seamless handoff that solves a problem engineers have wrestled with for over a century. Let us look at what forced induction means in real-world power terms. A naturally aspirated 2.0-liter four-cylinder engine might produce 150 to 165 horsepower. Add a turbocharger with a moderate boost level and that same 2.0-liter engine can produce 250 to 300 horsepower without any internal engine changes. Push boost further and you approach 400 horsepower from 4 cylinders. This is why downsizing has become the dominant engineering trend. Ford replaced their naturally aspirated V6 and V8 options in the F-150 with turbocharged EcoBoost 4-cylinder and 6-cylinder engines. Fuel consumption improved while towing capacity and performance were maintained or increased. The turbocharged 2.7-liter EcoBoost in the F-150 produces 400 horsepower and 500 pound-feet of torque figures. That would have required a much larger naturally aspirated engine a generation ago. BMW, Mercedes-Benz, Volkswagen Group, and virtually every major manufacturer has undergone the same transformation. The days of large displacement naturally aspirated engines as the primary performance solution are largely over in production vehicles. Turbocharging delivers more power from smaller, lighter, more fuel-efficient packages. Emissions regulations across Europe, North America, and Asia have made this shift not just commercially attractive but effectively mandatory. Here is the final counterintuitive insight. Many people assume turbocharged engines are inherently less reliable than naturally aspirated engines because of the additional complexity. Modern data does not support this. Before you go, if you learned something valuable today, hit that like button right now. Subscribe to AutoVision Daily for a brand new video every single day. We will see you in the next one.